Hi guys, this is Joshua LaForge here at Channel Islands High School, and today I'm going to be talking to you about rotational equilibrium. Rotational equilibrium is any time that an object is not accelerating in a circle. In order for an object to be not accelerating in a circle, in other words, in order for an object to be stopped and not spinning at all, or in order for the object to be spinning at constant speed, we need to know that all of the torque, the net torque, is equal to zero. In other words, in order to be in rotational equilibrium, an object has to be balanced where all of the torques are canceled by other torques. Let's try an example related to that. Okay, so here's our example. We're going to be imagining a meter stick that is balanced at the center. And on that meter stick are two hanging masses, one of 200 grams and another of 100 grams. Our 200 gram mass is 0.2 meters from the center of the meter stick where it's balanced. But we don't know how far our 100 gram mass is from the center of the meter stick. And that's what we're going to try to solve for in this example problem. Now, perhaps most importantly, we need to ask, as a good physicist, before starting the problem, we need to know, is this object accelerating? And of course, because the object is in equilibrium, because it's balanced, it is not accelerating. So we know that the net torque on this object is going to be zero. Alright. Anytime the net torque is zero, that means that the torque in one direction is canceled by a torque in the opposite direction. In this case, we have a torque clockwise and a torque counterclockwise. The torque clockwise comes from this 200 gram mass over here. On the other hand, we also have a torque counterclockwise that comes from this 100 gram mass. Of course, because the net torque is zero, the torque clockwise is equal to the torque counterclockwise. But how do we find out how much these are? Well, from previous videos, we know that the torque is equal to the force times the radius. Always. In this case, the torque is equal to the force of weight of these masses times the radius. And so we can plug in this equation to help us solve for both of these. For the torque clockwise, we know that our force is going to be 2 newtons times a radius of 0.2 meters. And therefore there's a clockwise torque that is equal to 0.4 Newton meters. On the other hand, we cannot solve for our counterclockwise torque yet because we don't know the radius, but we can plug in these variables. And then, since we know that the force of weight from this 100 gram mass is 1 Newton, we can divide this side by that 1 Newton and find that the radius up here is 0.4. Again, this is all made possible by our realization that this is not accelerating, and therefore the net torque has to be zero. Alright, in order to summarize what we've learned, I've got 3 key concepts for you. The first is, and this is true of any physics problem, we always want to go in and ask, is the object accelerating? If we find out that the object is not accelerating, we know that it's in equilibrium, and so we know that the torques will all cancel out. Usually that means that we have a clockwise torque and a counterclockwise torque that are canceling out. Finally, when we go to calculate those torques, we need to know that torque is equal to force times radius. If we keep all three of those things in mind, we won't have a problem with rotational equilibrium. So go ahead and try those practice problems, and I'll see you next time.